Bismillahirrahmanirrahim. Start with the name of Allah, the most gracious and the most merciful. My name is Isha Shafiq and I am from the Department of BS Chemistry. The topic of my presentation is Industry 5.0 and today I am going to discuss Introduction to Industry 5.0, Core Principles of Industry 5.0, Enabling Technologies, Human-Machine Collaboration, Challenges and Barriers, Future Trends, Case Studies and Conclusion are the summary of Industry 5.0. So let's start it. What is Introduction to Industry 5.0? Industry 5.0 represents a paradigm shift in industrial evolution, emphasizing the integration of human creativity and expertising with advanced technologies to achieve personalized, sustainable, and resilient manufacturing system. Unlike its predecessor, Industry 4.0, which focused primarily on automation and efficiency, Industry 5.0 reintroduces the human element at the core of industrial processes. Evolution from Industry 1.0 to Industry 5.0. The industrial evolution from Industry 1.0 to Industry 5.0 can be read as a sequence of technology-led structural shift that progressively increased mechanization, electrification, digitalization, and finally the recentering of human and sustainability in production. Each stage is defined by dominant technologies, organizational practices, and socio-economic consequences, culminating in Industry 5.0, human-centric, sustainable, and resilient manufacturing vision where collaborative intelligence, circularity, and social welfare are explicit objectives. Here are the differences from Industry 1.0 to Industry 5.0. Industry 1.0. Industry 1.0 include mechanization via water or steam power factory system emerge. Industry 2.0. Industry 2.0 include mass production and electricity enable assembly lines and economies of scale. Industry 3.0. Industry 3.0 electronics and programmable logic controllers bring automation and digital control. Industry 4.0 cyber system, physical systems, CPS, Internet of Things, big data, cloud computing, and AI enable highly interconnected, data-driven smart factories and value chains. The emphasis is on efficiency, flexibility, and automation. Industry 5.0. Industry 5.0 retains the technological foundation of 4.0 but reorients objectives, augmented humans, prioritize workers' well-being and human skills, designed for circularity and low environmental footprint, and built resilient supply chain and production system that can withstand shocks. This is a normative shift as well as a technological one. Characteristics: human-centric collaboration. Industry 5.0 promotes symbiotic relationship between humans and machines where advanced robotics and AI collaborate with advanced workers to enhance creativity and decision making in production environment. Sustainability and resilience. The framework emphasizes environmental sustainability and system resilience, integrating technologies like green computing and renewable energy sources to produce ecological footprint and enhance adaptability in manufacturing process. Customization and personalization. Leveraging technologies such as 3D printing and AI, Industry 5.0 enable mass customization and allowing manufacturers to produce personalized products efficiency without compromising on cost effectiveness or quality. Technological framework and enabling technologies. Industry 5.0 is underpinned by several key technologies that facilitate its human-centric and sustainable objective. Collaborative robots designed to work alongside human operators, keyboards enhance productivity and safety by handling repetitive or hazardous tasks, thereby allowing human to focus on complex and creative aspects of production. Artificial intelligence and machine learning. These technologies enable predictive maintenance, quality control, and optimization of manufacturing process, contributing to increased efficiency and reduced downtime. Internet of Things. The Internet of Things IoT devices provide real-time data collection and monitoring, facilitating informed decision making and resource optimization in manufacturing environments. Circular economy. practices. Industry 5.0 integrate circular economies principles and promoting the refuse and recycling of materials, thereby reducing waste and enhancing sustainability in manufacturing processes. Next, our point is Industry 5.0. Industry 5.0 differs technically from Industry 4.0. Objective optimization. Objective Industry 4.0 optimizes throughput, agility, and cost. Industry 5.0 optimizes a multi-objective function that include human well-being, sustainability, and supply chain resilience in addition to productivity. This requires multi-criteria decision framework and new KPIs. Human role. In 4.0, humans were often relegated to exceptions handling and system oversight. Industry 5.0 intentionally position humans as co-designers and co-creators using interfaces and collaborative agents that preserve agencies and skill development. This demand advances in human-machine interfaces, explainable AI, that is XAI, and socio-technical system engineering. Design for circularity versus linear efficiency. Industry 4.0 improved resource efficiency but left life cycle decisions external to operational loops. 5.0 integrates circular economy logic, reuse, remanufacturing, material passport into production planning and product design via digital twin and traceability system. Metrics and governance. Industry 5.0 required new measurement system and governance for ethical deployment of AI and robotics areas underdeveloped in 4.0. Standards and policy instruments are emerging to fill that gap. Here are the comparative analysis for Industry 4.0 and Industry 5.0 in the tabular form and also in the picture form. Core principles of Industry 5.0. Industry 5.0 or I 5.0 is the socio-technical evolution that layer three primary aims: human-centeredness, sustainability, and resilience or flexibility on top of the digital automation groundwork laid by Industry 4.0. The three pillars of Industry 5.0 are in this picture, where you can see people-centeredness, resilience, and sustainability. Human-centric approach. Human-centric in I 5.0 is repositioning the workers from being a cost factor to being a source of creativity, decision making, and value. The goal is to create systems that augmented human strength while taking over repetitive, hazardous, or ergonomically harmful tasks. Practical element: augmentation over automation. Design workstations and software that amplify human judgment, for example, AR or HMI overlays, assistive keyboards, and design supportive systems. Skill and upskilling, continuous learning pathways, and on-the-job training integrated with production systems. Digital twin for training and adaptive tutoring. Ergonomic and well-being metrics, sensorized workplace and human digital twin to monitor load, posture, and cognitive stress, enabling real-time adjustment to tasks and schedules. Why it matters? Because workers involvement improves system adaptability and reduce brittle automation failure modes. Because humans apply contextual reasoning that current AI or automation struggle with. Empirical studies and framework shows that human AI robot ecosystem outperform purely automated pipelines in tasks requiring complex problem solving and personalization. Sustainability and green manufacturing. Sustainability in I 5.0 is not an add-on. It is a design principle that spans material selection, process design, energy management, and product lifecycle. I 5.0 leverages digitalization to optimize resource flow, minimize waste, and enable product reuse or repair. Key mechanisms include process optimization using high fidelity models to minimize energy and material losses in real time, and design for circularity. Additive manufacturing and modular design that facilitate repair, remanufacture, and material recovery. Green supply chain, IIoT plus blockchain for provenance and traceability. Technical grain and evidence simulation driven scheduling and predictive maintenance reduce idle and scrap rates. Studies show measurable energy and emission reduction when digital twin are deployed for process optimization. Next point is core technical approaches. Digital twin enabled what if analysis, run high speed scenarios simulations to evaluate in alternative production routing and resource allocations during disruption, decentralized decision nodes, edge computing plus human oversight so local unit can continue operating when central servers or networks are unavailable, reconfigured keyboard cells and modular tooling, hardware designed for rapid reprogramming and redeployment to alternate tasks. Measured outcomes. Case studies and models indicate that combining human operators with adaptive digital twins and flexible Qbot fleet material shortens recovery time and reduces loss of throughput during supply or demand shocks. Next point is collaboration between human and machines. Collaboration means tight, safe, and meaningful interaction paradigm where human and machine share tasks, goals, and situational awareness. For I5.0, this spans physical collaboration and cognitive collaboration. Design principle: shared intent models. System that model the operator's intent and adapt assistive action accordingly. Transparent AI explanation, confidence scores, and human in the loop overrides. Safety by design, formal hazard analysis, and lightweight complaint actuators for physical keyboards, secure access, authentication, and fail-safe strategies for cognitive system. Next point is enabling technologies of Industry 5.0. Industry 5.0 emphasizes human-machine collaboration, not replacement. Personalized and socially sustainable value creation, circularity, and reduce environmental impact, and production systems that can quickly adapt and recover from the disruption. The movement is enabled by technologies such as collaborative robots, AI, or ML designed with human-centric principles, pervasive and IoT, digital twin, and simulation, additive manufacturing, and secured distributed ledgers and cyber security practices. Here you can see in the picture key enabling technologies are artificial intelligence, keyboards, 6G and beyond, digital twin, blockchains, IoT, big data, etc. Next point is advanced robotics. Advanced robotics keyboards are robots that designed for direct interaction with humans in a shared workspace. They emphasize safety, easy programming, and task adaptability. In I5.0, they act as physical augmenters of human workers. Key technical features: force sensing and complaint control for safe physical interaction, intuitive programming to allow shop floor staff to reprogram tasks quickly, plug and play modules, and standardize and effective interfaces for rapid tool swap. Application and evidence: assembly assistance, precise fastening, and material handling and ergonomic load reduction are widely demonstrated. Systematic review showed keyboard reduce cycle variability and can improve quality when integrated with human oversight and digital twin. Artificial intelligence and machine learning, AI or ML provide predictive maintenance, quality inspection and process optimization or adaptive scheduling and decision support. In I5.0, the emphasis shift to human-centered AI. Technical priorities for I5.0: interpretable model where operators can inspect and correct suggestions, human in the loop learning for continual model improvement using operator feedback and edge retraining, safe constraint optimization that inspect environmental and ergonomic constraints, representative results, AI driven visual inspections, Inspection system coupled with cubots reduce defect escape rates. Reinforcement learning can adapt robot control policies to human collaborators. Timing if trained with safety constraints. Internet of Things and Industrial Internet of Things. IIoT provide the sensor or actuator fabric for monitoring equipment, human inventory and energy flows. It is the telemetry backbone that powers digital twin AI models and decentralized controls. Next point is technical consideration. Edge computing for low latency control and privacy, interoperability via industrial standards to control or connect legacy machine and new cyber physical element security, because IIoT expand the attack surface application, real-time ergonomic monitoring, energy usage dashboards, condition monitoring for predictive maintenance and supply chain traceability. Third point is digital twin and simulation. Digital twins and simulation. Digital twin are high fidelity and real-time virtual counterparts of physical assets, processes, and or even human operators. In I 5.0, they are used for operator training, scenario planning, ergonomics evaluation, and sustainability optimization. Technical stack. Multi-physics models integrated with real-time sensor feed, simulation framework that allow physics simulators, control code, and human behavior model to run together. Human digital twin to model fatigue, posture, and decision tendencies so interference can adapt. Outcome. Digital twins can shorten time to adapt to new products, reduce commissioning time, and enable low risk training for operator interacting with new cubot cells. Experimental and review literature demonstrate measurable improvement when DTs are used. DTs means digital twins are used for scheduling and maintenance and optimization. Challenges. Qualification for safety critical component repeatability across printers and lifecycle assessment of materials remain as active research areas. Integration with digital twin in process monitoring is a common solution path. Blockchain and cybersecurity. Blockchain can provide immutable provenance record for useful for sustainability claim and complex supply chain. Cybersecurity is essential because integrated human machine need confidential integrity and availability guarantee. Technical trade-off. Permission ledgers are typically chosen for industrial use to control read-write access and reduce energy cost. Complementary measure hardware root of trust, secure firmware update channels, zero trust architectures, and an anomaly detection of using IIoT telemetry. Demonstrated use. Pilot project show traceable material passport for high value component and smart contract coordinating cross film workflows. However, integration and scalability across legacy system are non-trivial. Integration pattern. A few high architectures and patterns are emerging from the literature are given below. Human AI cubot cell plus local digital twin. Cubot assist operator sensor feed a local digital twin that run predictive checks and suggest operator action via AR. Data aggregated to enterprise DT for optimization. This pattern maximizes safety, low latency, and operator empowerment. For example, distributed resilient microfactories, multiple small reconfigurable cells managed by a resilient scheduler in the cloud with fallback at the edge for idea for personalization and local production. Human digital twin for training and well-being. Operator models used for shift planning, fatigue management, and adaptive task allocation tied to AI decision support to provide overloading human collaborators. Next, our point is trustworthy AI at the edge. Balancing model complexity with interpretability for operators, standardized human digital twin models, validated physiological and cognitive models that generalize across task and population, scalability, safety certification for mixed HRC system. New certifications and performance matrices are for collaborative cells across industries. Lifecycle environmental accounting integrated into real-time controls are moving from offline LCA to online control objective that minimizes emission and waste. This is the relation between collaboration between human and the AI technology or robots, cubots, which we say. Next point is human machine collaboration. Role of cubot in manufacturing. Collaborative robots or cubots are force or torque limited manipulators and control system designed to share a workspace with human without physical interaction, without physical separation, using complaint control proximity sensors and safety rated softwares. They are typically smaller, modular and easier to reprogram than traditional industrial robots. Typical task: precision assembly or screw driving insertion, machine tending, pack and place, polishing, deburring, visual inspection and metrology assistance, and ergonomic critical life lifting or holding task where the robot handles load while human does alignment. These roles shift human to supervisory and inspection in planning or exception task handling. Augmented reality or virtual reality assistance. AR is primary AR is primarily used for contextual step-by-step work instruction, guided assembly, and remote expert support, visual quality inspection overlays. VR is used mainly for immersive training, layout validation, and ergonomic simulation. Technical approach and architecture. Modern AR system in manufacturing typically combine a pose estimation pipeline, a low latency or rendering overlay engine, connectivity of MES or PLM or digital twin for live contextual data, and the last one is human input or feedback loop. Successful deployment integrate AR with the plant digital twin, so AR overlay reflect time and part state. Mechanism: workload or reallocation plus feedback loops by automating route calculation, search and constraint checking. System free human attention for higher cognitive tasks. Additionally, continuous feedback from AI driven analytics improve decision precision by surfacing edge cases and trade off rapidly. Human factors and skill requirements to actually gain creativity gains. Organizations must train workers in prompting and interpreting skills, maintain transparent AI output explainability, and provide psychological safety so workers treat AI output as aid rather than threat. Studies show creativity only when workers have autonomy and understood the tool limitations. Next, our point is risk. Over reliance leading to skill erosion and biased or brittle AI suggestions, and increased surveillance leading to reduced motivation, mitigation, regular human-led design review, red team testing of AI suggestion, and policies that preserve autonomy and privacy, AI or creativity when human automation and training present. Empirical study shows a positive effect on creativity and decision quality when only when humans operate, retain autonomy, and have training in using AI tools. Engineering and deployment checklist: pilot cell choosing a mid complexity assembly task, measure baseline KPI, cycle time, defects, and ergonomics. Next, our point is applications across industries. Automotive and aerospace. Automotive and aerospace sectors are prime target for Industry 5.0 because they combine complex supply chain, high energy, material intensity, and strong innovation capacity. Key opportunities include design for circularity, factories that integrate high level of automation with human robot collaboration for flexible assembly and green material substitution. Several large OEMs and piloting renewable carbon efforts and recycled feedstock as part of supplier decarbonization goal. Example: decarbonization production and materials. Are aerospace faces challenges with composite recyclability, and research and pilot remanufacturing lines have been expanding. Automotive makers are implementing closed loop material flows and for aluminum and plastic, and testing bio-based or capture carbon polymer in interior components. These efforts illustrate the combined strategy: material R&D plus process energy transitions and circular procurement. And industry reports show how measurable emission reduction when companies combine these strategies with supplier engagement and programs. Next point is industrial. Mhm. Human-centric precision and manufacturing. Healthcare benefit from Industry 5.0 human-centric orientation through personalized medicine and small batch manufacturing, advanced manufacturing, additive manufacturing, modular continuous processing, and closed loop quality control reduces waste from overproduction and accelerate time to treatment. Digital twin and AI improve process control in pharmaceutical continuous manufacturing, lowering energy and material waste. Reviews highlight that sustainable form of manufacturing combined with circular chemical management challenges, regulations, sterility and requirement, and quality assurance make circular approaches more complex in pharma. Nevertheless, process intensification and solvent recovery and are high impact levers widely supported by both academia and industry. Consumer good and electronics. Handling complexity and material recovery. Consumer electronics are resource intensive and feature complex multi-material assemblies that create recycling challenges. Industry 5.0 approaches combining design for disassembly, standardized and modular components, and digital product passport can increase recoverability for consumer good product as a good service. And models and circular business models are especially promising because they align manufacturer incentive with long productive times. Next, our point is smart cities with and infrastructure integrated system thinking. Smart cities integrate buildings, transport, energies, and industrial zones, creating opportunities for industrial symbiosis. Industry 5.0 Industry 5.0 technologies allow factories to participate and active energy or circulation nodes in city system, increasing resilience and reducing net urban emission. The European Research Agenda and Smart City project emphasize co-optimization across city sectors to unlock these benefits. Example applications: industrial waste heat used for nearby building or desalination, factory to grid service where flexible production schedules absorb variable renewable and circular Next is circular material hubs where multiple industries co-locate material recovery facilitate to share access to recycled inputs. Field studies and city scale pilots show that cross-sector collaboration can yield both emission reduction and cost saving when policy framework and infrastructure investment are in place. Next point is challenges and barriers. High initial cost and ROI uncertainty. Transition to Industry 5.0 recovery requires investment across multiple fronts, upgrading hardware, deploying industrial AI and digital twin, securing network, and is designing production for personalization and sustainability. Capital expenditures are often concentrated earlier in adoption cycle, while benefits, for example, higher customization, reduced waste, improved product value, accrued over time and are distributed unevenly across product line and customers. As a result, small and large size enterprises frequently face a high barrier to entry because they lack the scale and or financing to absorb upfront cost and the managerial bandwidth to run a parallel legacy return model system. During transition phases, empirical studies and market analysis continue to highlight cost as a dominant inhibitor to adoption, particularly where bespoke integration is needed or where legacy equipment must be retrofitted rather than replaced. Mitigation approaches: phased adoption, pilot to modular rollouts, and are using cloud or edge hybrid models to shift some CAPX to OPX. Cybersecurity risk and expanded attack surface. Industry 5.0 extend in human machine collaboration, interconnect devices at scale, IoT, and bring sensitivity, personal and operational data into workflows, increasing both the quality and quantity and sensitivity of data flow that in large heterogeneous attack flow include legacy OT systems. This is the challenges. There are challenges in these pictures and their solutions of Industry 5.0. Regulatory and ethical and supply chain vulnerability. Industry 5.0 emphasis on personalization and data-driven production, brings regulatory and challenges as well as ethical concerns, supply chain dependencies for specialized chips, sensors, or software create geopolitical and continuity risk. Recent review recommend robust governance structure, cross-functional compliance, and transparency mechanism to demonstrate traceability and ethical compliance. Next point is future trends. Industry 5.0 recombines human-centric values with technology capabilities. Below are four converging trends likely to shape adoption trajectories and research priorities across 2022, 2025, and into the near future. Personalization and mass customization. Industry 5.0 reframe production from mass uniformity toward value-driven personalization at scale. Digital twin, modular manufacturing cells, and AI-driven configuration engine allow for individualized products without linear increase in cost or lead time. Technique across include modular product architecture, parametric design, automation, on-demand additive manufacturing for low-volume variants, and digital job tickets that carry personalized specifications through production and inspection. Studies from recent years show that hybrid strategies mixing lean flow with localized customization cells as the viable path for balancing unit economic and personalization. Data-driven product configuration and human-in-the-loop design system enable customers and skilled operators to co-create variants while preserving traceability. This is the diagram for opportunities, limitations, and future trends or research of Industry 5.0. Next point is autonomous supply chain and resilient network. Autonomous AI-driven supply chain and leverage real-time visibility, predictive analytics, and automated decisions agents to dynamically reroute material, reschedule production, or switch suppliers in response to disruption. Industry 5.0 pushes this further by centering human supervisors for strategic decision while delegating routine replanning to autonomous systems. Research demonstrate gain in responsiveness and reduced downtime when human supervisors act as strategic arbiters and for ethical or commercially sensitive trade-off. For example, choosing between a slightly delayed but local supplier versus a fast international one. Autonomous logistic integrated with sustainability object carbon aware routing are also emerging. Next point is ethical AI explainability and responsibility automation. As decision authority migrate to AI system for personalization, schedule, and quality control, explainability and ethical governance are becoming non-negotiable. Industry 5.0 explicitly place human welfare and value at the center. Therefore, human system must be auditable, avoidable, and avoid discriminatory or unsafe decisions and enable human in the loop intervention. Emerging work recommends multi-layered governance and model provenance tracking standards for explainability and in operational context dynamic consent for personalization data and impact assessed for AI driven process changes. Reset academic review calls for cross-disciplinary team to co-design AI policies that are practical on the factory floor. Universal Robots Universal Robots has published hundreds of case stories where collaborative robots have been deployed to automate light assembly, pick and place testing, and ergonomically difficult tasks across SMEs and large manufacturers. Yours approach focuses on easy programming, safety, and safety in shared workspaces, in rapid redeployment between tasks, a pattern, and human-centered flexible manufacturing. Robots are the archetypal typal Industry 5.0 enabling technologies that they operate safely alongside humans are lower cost to trial than industrial robots and are often used to augment rather than replace human workers, enabling mass personalization and small batch production where human skills and judgment remain valuable. Numerous case stories show shop redeployment robots to relieve tedious tasks, improve ergonomics, and let skilled workers move to problem-solving roles. Next, our point is here is the practice loop of industrial big data for customized production process optimization diagram. And next point is Siemens. Siemens has moved aggressively aggressively to combine automation rollout with large-scale reskilling and people-centric learning program. Public Siemens case material and internal learning descriptions document program to upskill thousands of employees, deploy bottom-up digital learning, and embed people-centric design into automation adoption. Siemens and also publishes case material showing how reskilling reduces resistance and create internal capability to manage and scale automation safely. Industry 5.0 stresses that automation must be accompanied by workforce deployment development. Siemens example demonstrate a practical model. Treat people as partners in transformation, a template that other manufacturers can emulate. Academic review also highlight the necessity of this human-centric implementation architecture. Philips Healthcare automation that frees clinicians for patient care. Philips has a documented project where AI and automation free clinician from administrative tasks, speed image analysis, and enable remote assistant, delivering more time for direct patient care while improving throughput and diagnostic consistency. Philips case study as and trend report shows that real deployment that answer workforce shortages pressured by augmented clinicians rather than replacing them. Healthcare is a classic human-centric domain. Automation reduces clinicians' workload and improve access to care is a direct Industry 5.0 objective. Philips example shows cross-sector transferability of the human-centric automation model. Industry 5.0's summary. Introduction and overview. Industry 5.0 represents the next evolution of industrial transformation, emphasizing human-centric sustainability and resilience, and building on the automation of and digitalization grain of Industry 4.0. Unlike previous industries, revolution focused primarily on efficiency and productivity. Industry 5.0 integrate human creativity, AI, advanced robotics, and green technologies to co-create values. Key features focus on human-machine collaboration rather than automation, sustainable and environmentally responsible manufacturing, flexible, resilient, and resilient production system capable for mass customization, ethical and AI deployment. Evolution path. Industry 1.0 mechanization via steam engine. Industry 2.0 mass production with electricity. Industry 3.0 automation using electronics and IIT. Cyber physical system, IoT, and data driven automation. Industry 5.0 human-centered, sustainable, resilient, and collaborative automation. Core principle of Industry 5.0 human-centric approach. Humans and machine work as complementary partner. Worker safety, ergonomics, design, creativity, and decision making are prioritized. Sustainable and green manufacturing. Green energy efficient process, reduce waste, circular economy integration, carbon neutral production, resilience and flexibility, robust supply chain, and adaptable production system due to a respond to disruption. Collaboration between human and machines, AI, keyboards, and advanced robotics augmented human skills and rather than replace them. Enabling technologies, advanced robotics and collaborative robots enable safe physical collaboration with humans, reduce ergonomic risk and repetitive task burden. Artificial intelligence and machine learning, predictive maintenance, quality inspection, intelligent decision support, human in the loop AI ensure operator oversight and ethical deployment. Internet of Things and Industrial Internet of Things, real-time monitoring, process optimization, energy and resource efficiency, digital twin simulation, virtual replicas for scenarios testing, or process optimization, predictive maintenance, additive manufacturing, 3D printing enable mass customization and reduce waste and shorten supply chain, blockchain and cyber security ensure security and transparency. and resilient data management and transactions. Next point is augmented reality and virtual reality, enhanced worker training, assembly and guidance and remote support, automation across industries, automotive and aerospace, human robot collaboration, ergonomic automation, flexible assembly lines, healthcare and pharmaceuticals, AI assisted diagnostics, administrative task automation and freeing clinicians for patients, fair patient care, customer good electronics, consumer goods and electronic customization, production, small batch manufacturing, cubot and support assembly. Next point is human machine collaboration, cubots, augmented human workers, reduce repetitive strain and support complex tasks, AR or VR assistant, training, remote guidance and error reduction, enhance creativity and decision making, human focus on cognitive creative task and while machine handle repetitive operations. Seventh, challenges and barrier, high initial cost, significant investment in cubot, AI system and digital infrastructure, cybersecurity, increased risk, increased connectivity and exposed production to cyber threat, workforce training and skill development, continuous upskilling required for human collaboration, human machine collaboration, integration with legacy system, complexity in adapting new technologies to existing infrastructure, ethical and governance issues, ensuring AI and automation augment rather than replace humans. Next point is future trends. Personalization and mass customization, flexible production lines for small batch manufacturing, autonomous supply chain, AI driven predictive logistics and inventory management, AI driven predictive maintenance, reduce downtime through real time monitoring, ethical AI and responsible automation, over human oversight, explainable AI and transparent decision making. Industry 5.0 represents a paradigm shift from automation centered efficiency to human centered sustainability and sustainable industrial development. It combines cut edging technologies, cubots, AI and digital twin with human creativity, with ethical consideration and environment responsibility, creating resilient, flexible and future ready manufacturing ecosystems. Success depends on how carefully stage implementation, workforce training, sustainability and integration and a holistic approach to human collaboration, to human machine collaboration. And these are the references from where I have taken the data. And thank you so much. Allah Hafiz.